Welcome to the Quick Start tutorial for AFT Fathom. This tutorial will teach you the fundamentals of using and understanding AFT Fathom. Prerequisites include passing an undergraduate engineering course in the analysis of pipe system fluid mechanics. One must also have familiarity with standard industry practice in pipe flow analysis. AFT Fathom is a general-purpose tool for modeling pipe network hydraulics with incompressible fluids. Fathom calculates pressure drop, flow distribution, and optionally an energy balance for heat transfer. Fathom can model Newtonian fluids or non-Newtonian fluids using a number of different methods. Fathom models liquid systems and gas systems where the effects of compressibility are negligible. Fathom models open and closed systems, which can be pressure, gravity, or pump driven. Fathom offers customizable component and property databases.
Fathom has a number of additional add-on modules that enhance the user's ability to analyze a system. They include a goal-seeking control module, an extended time simulation module, a settling slurry module, and automated pipe sizing modules for both pipelines and pipe networks.
The engineering assumptions and limitations required to use Fathom include flow being steady state, all fluids are incompressible and single phase, all pipes must be liquid full, and Fathom can't model the effects of chemical reactions throughout the system. AFT Fathom is broken into 5 primary windows. The workspace and the model data windows are primarily for building and defining your model, while the output, the graph results, and the visual report are primarily for reviewing the results. Let's explore the workspace window in more detail. To build a model, you will be using the toolbox on the left-hand side of the workspace window. To draw a pipe on the workspace, simply click on the pipe drawing tool and then draw a line where you would like your pipe to be located. To place a junction on the workspace, simply click on the junction and then drag and drop it onto the workspace. To move a pipe or junction, simply drag and drop it where you would like to move it to. To move one end of a pipe, you can either move the connected junction or you can drag and drop the handle on the end of the pipe. To enter input data, simply double-click on a pipe or junction and a Properties window will open. The Properties window is the platform for entering data to define the pipes and junctions throughout your model. To help you identify the minimum required input data, we have highlighted those cells in blue. We will be disabling the blue highlight feature for this Quick Start tutorial in order to make data entry easier to see. To toggle the highlight feature on or off, you can double-click in the background of any Properties window. There is a model status light in the lower right corner which will turn green after you are ready to run your model. If you click on the model status light, a checklist will be displayed outlining what must be completed prior to running your model. The checklist can also be accessed through the View drop-down menu. The solution control is defined by default and the cost settings are disabled by default. We will discuss these checklist items in greater detail in a future tutorial. Your System Properties window is where you define your fluid data, your viscosity data, and your system data. In order to fulfill the Define Pipes and Junctions checklist item, you must construct your model in the workspace and fill in all of the required data for each pipe and junction. Now let's dig a little deeper into the toolbox. The Pipe Drawing tool allows you to draw pipes on your workspace. Keep in mind that every pipe must be connected to a junction at either end. The minimum required input data for a pipe includes the hydraulic diameter, the pipe length, and the friction model. To help you define your pipes, we have provided a pipe material database which allows you to select standard pipe materials, sizes, and schedules. The branch junction is used as a generic connection between pipes. You can connect up to 25 pipes to this junction. By default, this junction balances mass flow, so all flow into this junction is equal to all flow out of this junction. The assigned flow junction is a flow type system boundary. This junction allows you to define a volume or mass flow into or out of the system, and Fathom will then calculate whatever pressure is required to maintain that flow. The control valve junction allows you to maintain control at certain steady-state operating conditions. This junction can be modeled one of 4 ways. A pressure-reducing valve, where the user defines a downstream pressure. A pressure sustaining valve, where the user defines an upstream pressure, a flow control valve, where the user defines a constant mass or volumetric flow rate, or a constant pressure drop, where the user defines a constant delta P which the valve attempts to maintain at all flow rates. The heat exchanger junction can be modeled a number of different ways. You can define the hydraulic loss model of this junction as a constant K-factor, a tube configuration, or a resistance curve. If you enable heat transfer in the system properties, you can also model the heat exchanger using one of 11 different thermal models. The pump junction allows you to define how the fluid is propelled through your system. The minimum required input data for a pump junction is an elevation, as well as a pump curve, a defined flow, or a defined pressure or head rise. The pump configuration window allows you to enter a centrifugal pump curve as either a volumetric or mass flow rate versus either a head or pressure rise. To switch between volumetric or mass flow and head or pressure rise, or to change units, simply click on the drop-down arrow at the top of the respective column. Keep in mind that AFT Fathom is simply a tool that automates the process of solving fundamental engineering equations. There are a large variety of junctions available to you, each with unique features and many with overlapping functionality. The reservoir junction and the assigned pressure junction are examples of similar system boundary junctions. If you define these junctions the same way, they will give you identical results. The reservoir junction acts as a pressure-type system boundary, sourcing or sinking fluid to or from the system. The minimum required input data for a reservoir junction includes a liquid surface elevation and a surface pressure. The assigned pressure junction is also a pressure-type system boundary. This junction also allows you to define a known pressure and elevation, and as with the reservoir junction, Fathom will calculate whatever flow is resultant from that input. Now let's model the simple pumped cooling system shown below in order to determine the pumping requirements. The system fluid will be water at 70 degrees Fahrenheit. Notice that the system properties are now defined. Now we'll build the model using the toolbox on the left. Notice that as you hover over an icon in the toolbox, there are shortcuts that appear in the bottom of the left pane. If you hold down the Control key on the keyboard, you will be able to draw multiple pipes consecutively without having to re-click the pipe drawing tool every time. In the interest of time, I will only show how to define one pipe in this example. Pipe 1 is 200 feet of 3-inch Schedule 40 steel. If you are following along, please pause the video and enter data for all of the pipes in your model. All pipes are 3-inch Schedule 40 steel with the following lengths. You can speed the process of entering data for pipes and junctions by using the Global Edit feature. You can learn more about this in a different video tutorial. Alright, let's spot check a few pipes to verify the input data. You can review the input data of a pipe or component by right-clicking on it. You can also quickly review the input data by using the inspection window in the Quick Access panel on the right. All of the elbows will be defined as standard with the K-factor per the Crane Technical Paper number 410. Again, in the interest of time, I will only define one elbow. All elbows will be defined the same except for their elevations, which are shown below. Now we'll enter data for the heat exchanger, the assigned pressure, and the pump. Notice that the elevation is already defined. By default, Fathom will automatically populate the most recently used pipe size and material, as well as the most recently used elevation. In this exercise, we will only be modeling hydraulic losses for the heat exchanger. We will discuss heat transfer in a different tutorial. We will model the hydraulic losses using a resistance curve, which should be readily available from the heat exchanger datasheet. After entering data for the heat exchanger resistance curve, we will plot a second-order curve to fit these data points. This allows us to accurately capture different hydraulic losses for different flow rates. The assigned pressure junction will act as a pressurizer for the pump's suction. The assigned pressure will be located at 0 feet elevation with a constant pressure of 20 psig. The purpose of this exercise is to determine the pumping requirements. We know that we require 200 gallons a minute through the heat exchanger, so we will define that flow rate at the pump in order to review the pump behavior at that operating point. Notice that now our model is fully defined and we are ready to run it and review the results. At this point, many engineers will prefer to have a more consistent visual layout. It's easy to move text labels and rotate junctions on the workspace in order to make them look more aesthetically pleasing. Now that you are familiar with the workspace window, let's review the second input window, the model data window. The model data window is a useful tool to help you review the input in a text-based layout. It's easy to give your input a sanity check by scanning down each column and looking for the wrong units, or double-checking orders of magnitude. The input here is not interactive, but you can double-click on the row of the table corresponding to any pipe or junction and bring up its Interactive Properties window in order to modify any pipe or component input. Let's assume that we want our pump to operate at 80% efficiency. You must first save your model before you're able to run it. I have already saved this model as Quick Start Example. Now let's run the model and review the results. The output window looks similar to the model data window, except that now we are looking at the results of the analysis rather than the user input. Based on our input, we can see that at the desired flow rate of 200 gallons a minute, we need to have a pump that can produce about 120 feet of head. Using this data, we can then select an appropriate pump and enter the pump curve into our model. Let us assume that our goal of 200 gallons a minute was a conservative estimate, and that we would like to model an existing pump with the following curve data. We can see that our selected pump closely matches the design criteria. To finish out part 1 of this quick start tutorial, let's take a look at the pump curve plotted against the system curve. You can see that the intersection of the pump curve and the system curve occurs very near the desired flow rate of 200 gallons a minute. This concludes part 1 of the AFT Fathom Quick Start tutorial.